I don't like starting with dark things, so we are all gonna think that, when he was telling that Fray Luis de Leon was giving his lecture, let's all picture that suddenly Monty Python comes in saying, nobody expect the Spanish Inquisition. Okay, no dark thing, we are going, we are all here to get the joy of functional programming, so let's have it up. But anyway, indeed, I'm going to talk about an actual way you can use to build domain-specific languages if you have a language which supports continuations, or you have some way to get continuation in your language, which I will do in Kotlin, because it's like the language has somehow popularized having coroutines and continuations within the language. But actually, if you look at what is happening in the Scala world, they are also talking about like using more continuation, passing a style. You can do these kind of things in Haskell using continuation models. So kind of the technique, I want to show it in Kotlin because they pay my salary, so kind of it was an obvious choice from that point of view. Yes, this in theory could happen, could work for any language with continuations. And to use this, I really love playing trading card games. And I used to actually use real trading card games, but my wife decided, you should have like things with cats. Because from her point of view, we do things with cats, whatever. Many of you may have played at this kind of thing. You have cards and you have like kind of monsters or sorceries or whatever, and then you want to defeat the other ones, and then you have like attacks, and this attacks the damage, and the usual thing when you do enough damage to the other monster or player or whatever, then this is discarded or this dies or whatever. Depending on the different language, on the different games, this kind of changes a bit. But I'm gonna use this kind of game as an example here. So as I said, what we are gonna do is we want to model this. So we are gonna assume that we are building a client or whatever. We don't care that much about the network or anything. All that we want to do is being able to model the information in a card in our programming language, so then we can execute it, do whatever we want with it. So for this, I'm going to use a simple data class, case class for the people doing Scala, just a record for people doing other languages, just a name, a list of powers, which are these things like you need to water energies or whatever you want to call. Again, that depends on the game. And then there is some damage, which is like how much damage you do to the opponent, like 10 or 20. So I have here like this is my Loch Ness monster cat. So it has an attack which is called Tsunami, and then it costs this amount of energy, and it makes 50 damage. So far, so good. If you haven't played any of those games, you will actually think, those games must be really, really boring. Like, what's the point? The one who has the biggest monster just wins, right? That's enough when you are like a 7-year-old and it's all super dramatic. But actually, people like to do more interesting stuff. So if you play these games, things usually happen like, you are going to flip a coin until you get tails. So, whoa, how many times? We all know that you are just going to get, half of it, and we can actually compute how much you want, but it doesn't matter. We want to model this thing. Like damage is 20 times the amount of heads you get. Or flip a coin, and if you get tails, this attack does nothing. Or draw a card, and if it's this kind of card, then you have to discard it, or do whatever. So the point of those games is by combining these cards, then you have a card which says discard a power card, and then another card which says, if you discarded a power card, then you win the game, and then that's what people do. There are actual championships you can watch on Twitch about this. They are nice. I like them, as you can see. But the point here is that we actually need to extend the model, right? Like what we had, where an attack is just a number with a damage, is no longer enough. Like we need to have a way to say, draw a card or discard a card. But even more so, we have things like flip a coin, and if the coin is heads, do this. So we need some kind of conditionals. And we even have some kind of loops. flip a coin until you get tails. So we can think of this as again, some kind of loop where you try to do something until some condition, in this case, is no longer true. So we need to have a way to do this. And to do this, essentially, we are just going to model this as more basic records. So what we are going to do is we are going to introduce this action type. That's the way you model this in Kotlin, is usually by having some interface and then having a bunch of classes extending this. So this is not very different from how you would, for example, do this in a Scala, where you have maybe a bunch of cases for a single parent class and so on. So that's how we're going to start. So now we have an action, and we definitely know that doing damage is one of those actions, right? So like somehow the output of an attack can be do this damage. So we are going to model this. But taking this idea farther, we can do like things like flip a coin, and then a flip a coin essentially gives you two branches, like what you do if you get tails, what you do if you get heads. So you can model this just as two elements to the record. And I don't want to go into much detail. It's actually nicer for all of these to, instead of just having two actions, which will be these two branches, to actually have functions which give you the actions to perform. I don't want to go into the details, but that's something which is actually going to be important later on. But the idea here is, again, if you think of a flip coin action, what you need to say is what to do when you have head, what you go to get when you get tails. So it's just those just are other actions. So for example, if we have this attack which says flip a coin, if we get a tails, the attack does nothing. We can model this as saying, well, this action is a flip coin action, has two branches. In the case if it gets heads, then we will do 50 damage. If it's tails, we can model do nothing as we do 0 damage. That's a way we can do this. And by the way, if you ever look at this kind of thing, this is very close to what people do in compilers call an abstract syntax tree. This is essentially kind of creating a value which represents a program, except that the program now is just text on a card, on a trading card game. So with this, you can already do things like executing one of these attacks, one of these small programs. This is essentially like an interpreter for our program. We can execute, one way we can execute this is, for example, to actually like flip a coin, which of course in our case means get a random boolean. Then if it's true, that means you got heads, so you keep executing the heads part. If you get a false, that's a tail, so you keep executing the tails part. So this is essentially giving you a way to have this program and run it. I just want to mention that running this is actually one thing you can do. You essentially have the program, so you can try to do more things here. Like you could imagine, try to give the average damage you do here by averaging both branches, or counting how many coin flips you need to do to execute this attack, to do them all at once when you are running your program, things like that. So once you have the program, my point here is once you have the program, you have the power to know things about the program. You can look at it, you can analyze it, you can even optimize it, right? Like why you make two conditions which are depending on the same coin flip. Well, you don't need to nest them, you can do this all at once. These kind of things are things which maybe for such a small language don't make much sense, but if you think of a bigger language, all these things may be important for you. And as I said, the other thing we also want to do, so coin flips are essentially conditionals, but we also want to do loops. So for example, here, this attack I said where you flip a coin until you get tails, and then, well, you do 20 times the amount of damage. So we don't have loops, and that is going to be a problem. That's one of the things we're going to solve. But we, by the way, can do something now if we use recursion. So we kind of have here a recursive function which keeps some accumulated damage, and then we start at 0, and then we say, we flip a coin. If it's heads, then we recur, right? We recur, but with more accumulated damage until the point in which we get some tails, and then we return this accumulated damage. So this is essentially doing the same thing as this program. But we can already see that I needed to talk a bit to convince you that this is doing the same thing. Like, this is not a direct translation. And we can add more actions. We can add discarding thing, draw cards, all of those things. What I want to point is that you always have the same pattern in which you always have some next actions and something to do next. In the case of the coin flip, you actually had two different branches, what to do when you have heads or tails. But in the case of, for example, discarding a card, you will discard a card and then do something later. So you can model this always as a final next field, which tells you essentially how you proceed with the next actions. Good, so you can write again examples like this where you say draw a card. If it's not a power card, discard it. So you can say, well, draw a card. This will actually, you need to tell what to do next, and this actually will tell you which card you draw, and then you say, well, if it's a power card, then, well, you keep the card, and then you do 0 damage, and then you are done. Otherwise, you discard it, and then do 0 damage. 0 damage is really like do nothing, as I said before. Anyway, what I really wanted to focus here, and that's where continuations enter the game, is that all these operations like flipping coins, discarding cards, drawing cards, always end up with this final next field, which says what to do next. And that's actually like how to continue with the program. That's what we will call the continuation. One trick we can actually play to have everything exactly the same pattern is, in the case of flipping a coin, we said we have a branch for heads, one branch for tails. We can say, well, instead of that, we will have just one branch, but we will give you as information what happened. So we have this flip outcome, which is head or tails. So the continuation you use will get the information about what was the result of the coin flip, and then you will tell me what to continue. But because you have the information, you can give me different answers depending on the different outcomes of the flipping. And then the second thing I will do before continuing is that we had this damage, which was like always an integer. To make things a bit more general, and this will help us later, we will actually replace all of these by any generic result type. So damage is an integer, but you could imagine that, well, you get back a boolean or you get whatever. So it's just easy to introduce this done instead of damage. I'm just, like, if you move from one to the other, it's the same thing, except that the damage is now done of A. So you have this generic parameter, and this has like a domino effect, and everything now needs a lot of brackets with A. But essentially, that's the idea. We are just going to have a computation which is doing a bunch of things. Each thing has a continuation which says what to do next, and at some point you are done, right? We finished our program. Good. That's actually what this other talk that Carlos mentioned was about like talking about this but longer. So I already mentioned this. This kind of writing program is great if you want to analyze the program. Like, this gives you all the information. So we can write actually a lot of ways to execute this, but as I said before, it's possible to optimize and analyze the program even before running, because you have the shape of the program. The bad thing is that this thing where we had to like make a recursive function when we wanted to make a loop, it's kind of hard. So you imagine that we are giving this program to the people who are actually creating the cards. Like, these are, there are people who know very much about how you make a balanced card game and all of that. And then you ask them, but every time you are gonna think of a loop, why don't let me introduce you to recursion, right? It's something that everybody knows about. And the second problem is we haven't shown it too much, but things start to next, because the thing to do next is a function. So you nest a function, you set a function. All of this is very ugly. What if we could write something like this? So that's actually our what we would like to do. We just want to say, you flip a coin, and then you say heads or tails, 50 or 0. That's like a straightforward translation of the attack. And for the other one, well, we keep a counter, but we now really have a loop, right? We say, while the flip coin is heads, we add 20, and when we are done, we return the damage. That's a more straightforward translation. You could even imagine having something which, instead of accumulating the damage, just adds 1, and then it multiplies 20 by the amount of heads. That maybe would be even more straightforward. So the question here, and the point of the talk is, can we get this syntax? And the answer is actually yes. You already know how to do this. Like, it's actually quite a stupid thing. Like, sure, can we make this type check? Yeah, well, okay, yeah. Let's say that we have we have an interface. I'll call it an action scope. Name doesn't matter, which has this flip coin operation. Don't look at the suspend yet. Has the flip coin operation, and then this program will already type check. We don't know what it does because it programs against the interface, but it is already working, right? So if we introduce interfaces, it looks like we can just write this program and at least make the compiler happy. And even if we want to execute simple things like executing before, it's also simple. Like, you just say what to do when you flip a coin, and then when the program is executing, it will call the implementation from the interface and just run this piece of code and do this. So you can just say, well, I create my stateful action, which is like the runner, and then I execute the action I want. And I'm using some niceties from Kotlin, like the fact that you can extend functions and call it that way. That's not super important here. Now, this is what we call the final style of modeling operations. But I didn't mention, but the other style is called initial style. So this is the final one, where you use interfaces to model operations. And this is always something I get, like, what is the point of doing? Like, okay, you have spent essentially 15 minutes to tell me that you can use interfaces to program. Thank you. I knew that maybe the first month when I started doing my programming, until you're like me and I started doing Pascal, which doesn't have interfaces. But this is actually a big deal in other programming languages. Like in Haskell, to do this, you need to introduce a type class or a type constructor, something which looks more like the Katz effects approach. So actually doing this in a language like Kotlin is like simpler. In other programming languages, it's actually the opposite. Like the initial style is going to be super simple to model, and the final style is harder. So I don't want to make it like one is super simple always. It's like it depends on the language you are using. Anyway, we're in the easy case, which is nice because that means that we don't need to understand all of this concept in top of what I want you to understand, which is continuations. So just to summarize all of this, like we've seen that this approach of using interfaces is great to write things. It actually is much more clear for the reader of the code of the program what we want to do, and it's very natural in some subset of languages, like languages object orientation, which is actually like the languages most of our will be using more than a pure functional language with type class and things like this. This is also relatively easy to extend, by the way. I'm not going to dive to this, but that's also a good thing of this. You can essentially have an interface which extends the other interface, and this is essentially extending your language. But the bad thing is, okay, it was easy to execute this, but this thing is really hard to inspect in some way. You can execute this, but you're essentially giving out control to the program, which then eventually will call your primitives. But if you are analyzing, if you want to optimize things, you don't want this. You want to be able to look at the program and change it, right? And this is something this is not possible so easily. I don't want to say it's impossible because there is this guy Olki Saliv, which actually managed to somehow do this. You can read his website. Is a wonderful thing. But I think that you can manage is not the same as it is easy to do this, right? So what we would like is we want it all, right? So what we want is to use the nice syntax to write our programs, or for our DSL users to write our programs, but we want, as the person get in the program, we want to be able to analyze it, to look at it, to execute it, to optimize it. And again, I'm repeating all the time analysis and optimization, but imagine when I see this DSL that you are building something like a DSL for SQL queries. In that case, optimizing is really great. You can see that people are maybe doing something which could be done in just one pass, then you optimize, and then your query to the SQL server is way more optimized. So these things really can pay off if you want to do this. So what we are going to look for is to essentially have a way to go from something which is a function in the final style, which is going to be this argument. This argument is just a function, and that this is Kotlin syntax to say, by the way, this action scope is going to be inside available as the this. So it looks like you are extending the action scope, sort of. And then you get back the action of A, which if you remember was the initial style. So it's the one where we are using data type. So if we get this, we would be happy, right? People would be able to write the block in the nicest style for them, and then we convert it to the action of A, and then we are happy because we can inspect what we need. So we can actually do this if we add this suspend thing, which is actually what brings coroutines and continuations into all this game. So let me briefly talk about what suspend does in Kotlin and what coroutines are all about. So the idea is that in Kotlin you can mark functions with this suspend keyword. That's like a keyword, and then and you can essentially think of it as a bit of like the async await paradigm. Is like you mark it as an async. But the main change is that when you call it, you don't have to mark the await explicitly. You just call it, and if it's suspended, if the entire function is also suspended, then you can call it. Otherwise, it will tell you I need like a suspend context for all of this to work. So that's kind of the thing. But what is going to be important here is not so much how the rules of the language work. It's going to be how it actually is compiled down. When this is actually executing. So this thing is actually be transformed into some form of callback style program, where instead of like so you say suspend and you return a byte array, but actually this program under the hood, and this function under the hood is returning nothing. It's like unit is like the unit in other languages, the void in languages like Java. And then instead of giving you directly the byte array as a result, you need to pass the function which takes this thing and does something else. And again, this is what we will call a continuation. And maybe you are starting to see how, the fact that we have something which is a next and does something is starting to make these two things look closer to each other. So in general, I'm going to tell about how we used it, but let me just stop for a moment to understand why having these coroutines is actually useful at all, and why like the people who design the programming language decide to introduce such a things that there's such a feature in the language, like or why actually make a special keyword for this and make the compiler do the transformation. The main thing about having this continuation and this style of coroutine is that this gives you control over when and how you keep executing. And the main use case for this is actually to implement something like concurrency. So if you do Kotlin, when you want to do concurrency, you often use this library called Kotlin X Coroutines, which implements what we call cooperative concurrency, cooperative scheduling. But the idea is the following, right? If I have a way to know how and when things are executing, and this is done because in this framework, you are the one controlling the continuation, right? So you, instead of just giving a continuation saying just keep going, you can say, well, at that point, let's get back control to somewhere else. This is a way in which you can implement this scheduling, because there can be a scheduler which has a bunch of things running, and then it executes something up to the point where it says, okay, now, now it's a point where I have done something, and you need to tell me how to continue. At that point, you can say, wait. Let me get back to the scheduler, and let's think, okay, I have 4 threads here. Okay, I will put this maybe in another thread and keep scheduling, or put it on a queue, or just decide, well, this is not fair, so it will go to a forbidden set of computations queue where it will only do it after a minute. So the point here is by having this point in which we can control when and how to keep executing, this opens the door for things like a scheduler to decide what to do, where threads to go, and so on. So this is the main use case, but what I'm going to show here is that apart from this main use case, you can use the same idea to implement this transformation from final to initial style. Good, but there is only one problem. To do this, we need to get the continuation. That's going to be part of it. But the syntax in Kotlin actually hides this, because I already mentioned that you use suspend, and this is transformed into, well, in a further layer in the compiler into this function, but this suspend thing on itself doesn't have a continuation argument. So we need a way to actually kind of dig in and get the continuation out of a suspend call, which is actually, for the further layers of the compilation, it's nothing, it's just returning the second argument, but in the surface language, the language we use, we need something extra to be able to do this, and this has this name called suspend coroutine. This is essentially just a way to get the value. So it has a very fancy type, but essentially it says, well, if you have something which is suspend, and instead of just using other suspend functions, you at some point want to really get the coroutine and decide by yourself when you are continuing with the coroutine, you can do this by calling suspend coroutine, and then you have to give it a lambda, a function, an argument, so they will give you back the k, that's the continuation, and whenever you want, you can call resume. And this is very useful, for example, when people want to interoperate between other kind of reactive systems, when you can use the suspend coroutine to say, oh, I get the continuation, and I only get it when a Scala feature is done, I call the coroutine continuation. So this allows you some interoperability. But from our point of view, essentially, this suspend coroutine is going to be kind of a keyword to get the continuation out of a suspend function. Good. So, yeah, it's nice because we are almost there. We actually have all the tools. We know what we want. The initial style, which remember meant that we are defining our program as a bunch of data classes, case classes of records of things which are nested. We have the final style, which meant that you want to model things in interfaces, and we want to move from the final to the initial style because this gives us, well, the characteristics we want for what we want to do. And we are going to use coroutines to do this. So bear with me. One thing is that this actually requires like 3 different things working together, and they don't fit all in a slide. So I have sequential slides, but hopefully by the 4th slide where I go back to the first one, the whole picture will be done. So if in the middle you're in a state of confusion and you say, I don't know what is gonna happen, just wait for a second. That's actually just a problem we don't really see that well because we are all day in front of a screen, so I cannot have like 10 point font. So yeah, it's actually your fault, not mine. So what we are going to do is follow with this path. So we are going to start with this thing we want, right? The final style, but we are going to instead this function called an interface. We are going to mark all of them with suspend, because that means that the compiler will make this transformation from us in which we can take the continuation. Then we are going to have a variant of action in which we are going to replace our continuation with functions, with continuation from Kotlin, and then we will be done at some point. So let's see. So the first part is the one actually in the middle. So we're going to have something which again looks very much like the initial style, but this continuation where we have actual functions are going to be this built-in continuation from Kotlin. And this is almost the same thing, except that before, what we had is you take some arguments and then you give back another continuation. But this continuation from Kotlin, you have something, but then you always give back unit. Is that you always let whatever happen. You don't want to produce anything. You don't care about it. So that's the part we will need to bridge. So we're going to actually implement one of these action scopes. So we are going to have an implementation from the interface. That's how we are going to execute the final style computation. And we have a careful interplay between two things, between like the coroutine system and a piece of a state that we will need to keep. And this piece of a state is actually going to be one of those things. It is going to tell us what the next action is going to do. So you can imagine, actually, I think a graph, something like this. So we will start doing the stamp action, then we will get to the flip coin. The flip coin will set the state to flip coin, and then at the other side we have the execution function will essentially read this state and produce one piece, like the top level piece of the program. And then at some point, and I will show how, the continuation inside the flip coin will resume, and then this will go back to the suspend the stamp action. That's the program we want to execute, and it will continue executing until the next action, which in this case maybe will be another flip action, and then we will set the state. And then at that point, this other thing will continue and will read. And you can see that there is a careful interplay because we have to be very careful of, at that point, reading and only executing enough so that we, if we did something wrong and we executed 2 flip coins, then we would be missing something, right? Because at that point, the state will be only the second one. We will be like mutating something we shouldn't be doing. So this is the careful interplay between these 3 things, like the current top-level thing we want, the things that actually execute this, and the suspended function, which represents your program, that will make the whole thing kind of fly. So the graph are nice, but I can also show you the code. So as I said, we have an implementation of the interface, which just sets the next thing to do. So in the case of flip coin, we'll just set it to the flip coin state, and in the case of discarding, we'll set it to the discarded state. But it will also keep the current the next continuation. That is the change we made. So we are gonna save this and decay. So at that point, what happens is that we are stopped. We know the next thing that will happen, like the next action that we need to produce, but also we know how to continue the rest of the program. And then we will have the execute, which will essentially look at the other way around. We'll just look at the current state, we'll produce one piece of the thing. So if the state is done, it will produce the done, and then it's actually finished. If it's flip coin, it will produce the flip coin constructor, the flip coin case. And then remember that I said at some point the fact that there is a function there is going to be very important, because the function means that we don't, until we call the function, we don't do anything inside, and that's what it's gonna stop in the graph until we get to the next point. So at that moment, we can grab the continuation from the flip coin state, and we can just resume it. And that will be the interplay between these 2 things. The only thing that it's missing, and I will go try to go not too deep in this, you need to somehow also start the domino chain. So you need to have a special way to start the coroutine in Kotlin. So for those who know Kotlin, there is the start coroutine, which is like, oh, please start executing the coroutine, because otherwise, like, how do you even start? So you need a bit of complicated code, because you need to start the coroutine. Then on the first kind of on the operation, you will stop until execute, and this will create the loop. And then at some point you are done, and this done of the coroutine is marked in a special way, but like last argument to the start coroutine, and in that point, you know that you have to produce the done case because you are done with this program. So again, you get something like this, except I'm not showing here. At some point, you get to the end of the coroutine here, and then you produce a done in that part. Of course, all of this is a lot of boilerplate. I spend my weekends when I'm bored writing things which automate boilerplates. That I guess what I do. I like writing compiler plugins. So there is one which does this. It's called Inicio, whatever. But what we've seen here is that there are these two ways to model our programs. When you want to do a DSL, the initial style, which is super great for analysis, the final style, which is super great for users. And by using coroutine, as I said, anything which has continuation can actually model this in a similar way. We can bridge the gap and get the ease of use of the final style with the initializability of the initial style. And yeah, that's it. If you want to talk about Monad, come later, because he showed me that I need to I don't have time to do this. Or ask a question. That's like a trick. And if instead of talking about this, I would have actually said the thing I should said in the slide, I would have said it instead. Whatever. I wrote a book. So that's it. Thank you.